Quantum mechanics is a fundamental theory in physics that provides a description of the physical properties of nature at the scale of atoms and subatomic particles. It serves as the foundation for various branches of quantum physics, including quantum chemistry, quantum field theory, quantum technology, and quantum information science. This theory has reshaped our understanding of the fundamental building blocks of the universe and the behavior of matter and energy on the smallest scales. Before the development of quantum mechanics, classical physics successfully described many aspects of the natural world at macroscopic scales. However, classical physics proved inadequate when applied to phenomena occurring at the atomic and subatomic levels. Quantum mechanics emerged as the solution to this challenge, offering a new framework to understand the behavior of particles at the quantum scale. Key features and principles of quantum mechanics include quantization. In quantum mechanics, certain physical properties, such as energy, momentum, and angular momentum, are quantized, meaning they can only take on discrete, quantized values rather than continuous ones. This quantization is a departure from classical physics, where these properties could vary continuously. Wave-particle duality. One of the most striking features of quantum mechanics is the wave-particle duality concept. Objects at the quantum level, such as electrons and photons, exhibit characteristics of both particles and waves. This duality challenges our classical intuitions, as particles like electrons can display interference patterns typical of waves. The uncertainty principle. Formulated by Werner Heisenberg, the uncertainty principle states that it is impossible to simultaneously know both the precise position and momentum of a particle with perfect accuracy. The more precisely we measure one of these properties, the less accurately we can know the other. This inherent uncertainty at the quantum level is a fundamental aspect of the theory. Quantum entanglement. Quantum mechanics introduces the concept of entanglement, wherein two or more particles become interconnected in such a way that the state of one particle instantaneously influences the state of the others, even when separated by vast distances. This phenomenon has been experimentally observed and is one of the most puzzling aspects of quantum theory. Quantum mechanics has been highly successful in explaining and predicting a wide range of phenomena, including the behavior of atoms and molecules, the nature of light and electromagnetic radiation, and even the gravitational interactions at quantum scales. It has enabled the development of numerous technological advancements, such as lasers, transistors, and nuclear power, that have transformed modern society. Despite its remarkable success, quantum mechanics challenges our classical intuitions and leads to profound philosophical questions about the nature of reality. The famous double-slit experiment, where particles display wave-like behavior, and quantum entanglement, with its apparent non-local connections between particles, are just two examples of the puzzling and counterintuitive aspects of the quantum world. As scientists continue to explore and research the quantum realm, they uncover more about the intricate and enigmatic nature of reality, and the classical physics world is built upon this kind of intuition. In the classical realm, you throw a ball, and you can predict its trajectory with accuracy. You can measure its position and velocity, and these measurements align with your everyday experiences. However, when it comes to quantum physics, things take a fascinating turn. At the quantum level, our classical intuitions no longer apply. Imagine trying to predict the exact motion of a quantum particle, like an electron, with pinpoint precision. It's as if you're trying to predict the future with a crystal ball that keeps shifting. The inherent uncertainty principle, proposed by Heisenberg, tells us that the more precisely we try to determine a particle's position, the less accurately we can know its momentum, and vice versa. This uncertainty is not due to limitations in our measurement tools. It's a fundamental aspect of quantum reality. Nature herself is inherently uncertain at the quantum scale. You can think of it as a cosmic game of hide and seek, where particles like electrons dart about, but you can't know their exact location and speed at the same time. It's as if the universe keeps some of its secrets locked away. Quantum mechanics introduces the concept that, until we make a measurement, particles exist in a superposition of states. It's like your cat, which could be both black and white simultaneously, until you check. So, you can't say definitively whether the cat is black or white until you measure it, applying mathematical operators to its quantum state. When you do, you get a specific outcome, but only for that moment. If you repeat the measurement multiple times, you'll see a distribution of results, with one outcome being more probable than others. Now, consider a collection of these quantum particles, like the atoms and subatomic particles that make up your coffee maker, your phone, or your car. When you have a large number of them together, their quantum weirdness tends to average out, and they collectively behave in a way that aligns with classical physics. This is why the coffee maker that relies on the collective behavior of countless atoms and electrons doesn't behave unpredictably. However, when you zoom in and study individual particles, that's where quantum mechanics takes center stage. It's the realm of uncertainty, probability, and wave functions. So, while your coffee maker functions as expected, the electrons within it dance to the quantum tune, guided by wave functions. But how do we reconcile this bizarre quantum behavior with the reality we experience every day? Well, quantum mechanics has proven itself to be a powerful and precise framework for understanding the quantum world. It's a theory that allows us to make accurate predictions and build technologies that have transformed our lives, from transistors in our devices to lasers in medical procedures. So, in a nutshell, quantum mechanics is the science of the very small, the atomic and subatomic world where particles exhibit both wave and particle-like behavior, where uncertainty reigns supreme, and where the act of measurement collapses superpositions into definite states. It's a theory that challenges our intuitions but has revolutionized our understanding of the universe. From the simple and elegant Schrödinger equation to the mind-boggling double-slit experiment, quantum mechanics is the key to unlocking the mysteries of the quantum realm. Quantum mechanics remains one of the most fundamental and essential theories in the physical sciences, shaping our understanding of the universe at its most fundamental level. Thanks for watching. Please subscribe to Good to Know.